Okay, y'all, so I seem to actually understand how mod for counter works, so I'm gonna help y'all try to understand this. So for the homework, we're obviously making a mod 8 counter, but I can't help you exactly with the mod 8 counter, but if I can help you understand the mod 4 counter, the mod 4 counter is basically the mod 8 counter, but one less input and output. So over this slide, a counter has a clock input and a reset input. Reset basically just resets the counter, but it can also break on you, so be careful with that. Well, that's like physically when you do it in Logisim, but for the concept, it works. Like, it's just resetting the value. And then a counter has a clock input because the clock input is what helps the counter go up in value. Here we have a mod for counter. It's kind of confusing, but this right here is one of our D flip-flops, and here's another one of our D flip-flops, and it has our inputs are the S1 and S0 selector lines, and our outputs are the Q0 and Q1 values. This is kind of hard to understand if you don't know what is actually going on. So, like, to understand how this works, it's better if you just move on to the state transition diagram. So for this, we have four states for our 4 different outputs, because if you think about mod 4, what that means is we have 0, 0, we have 0, 1, we have 1, 0. Sorry, this is kind of small. Let me make that bigger. Oop. Sorry. So how mod 4 is, it counts from 1 to 4, right? So we have our 0 state, 0, 0, and then if you add a bit, it's 0, 1, 1, 0, and then 1, 1. If we add again, we'll get 0, 0 again, right? So that's how it keeps going in the counter. So that's why here we have 4 different states you can be in, because 0, 0 is just going to go back to 1, right? So that's why we have A, B, C, D. Now if you think about mod 8, we have 3 lines, because if you want to count all the way up to 8, 8 is 1, 0, or if you want to count all the way up to 8, you have 1, 0, 0, 0, right? Because 1 plus 2 plus 4. Oh, me stupid. Yeah, it's 1, 0, 0. So that's why we have 3 for mod 8. So if you just think about that, you'll get it. So we have our output 0, 0, which corresponds to that one, 0, 1, which corresponds to that one, output 1, 0, which corresponds to that one, and output 1, 1, which corresponds to that one. So since we're always counting up by a bit, from A, if we want to go from A to B, we're adding a bit to 0, 0, right? So that's why here it's 0, 1, and that's how we go to B. And then from B, if we count up 1, we're going to have 1, 0. So that's why we go to C. And from C, if we want to go to D, we count up by 1, so we have 1, 1. And then for each of these states, let's say something happens and you add just enough where you go back to 0, 0. So then you'd all have to go back to A, right? But if you're counting up, you can't really go backwards, which is why we can't go from D to C or C to B. But everything connects to A, because if you manage to add up enough, you'll go to 0, 0, right? I don't know exactly how that works, but it works somehow. And the reset value is, it can be 0 or 1. And if it's 1, our other 2 values will always be 0, 0. So that's why there's this loop back to itself, because if the reset value is 1, it's always just going to stay in the state A. So that's why it has to be 0 for the reset value for B, C, and D to like keep moving on. I hope that makes sense. So if you think about this, with mod 8, we're going to have a lot more outputs, so there's going to be a lot more arrows. State table for mod 4 counter. So as we saw, we have our 4 different states, A, B, C, D, and then we have our reset value of 0 and 1, because that's the only 2 values it can be, right? And as I said just like 2 seconds ago, if the value is 1, it's always going to stay in state A. So no matter what you add to it, the bits don't matter. If our reset value is 0, from A to B, we add 1 bit. So that's 0, 1. B to C, we add another bit, that's 1, 0. C to D, we add 1 bit, it's 1, 1. And D to A, because after D, you just go back to 0, 0. So that would be back to A. So if thinking about a mod 8 counter, you'd have a lot more states, as I said previously, and these will all keep going until eventually your last state will point back to A. State assignment for mod 4 counter. So again, this is similar, except we're just saying what state it starts in this time. Like from the previous one, it's pretty similar, like the graphs. It's just we're stating what our starting. And then obviously 0, 0, add a bit, it's 0, 1. Don't know why it's twice here, but I think it's because we have Q1 and Q0 as our two outputs, so I think that's why. And obviously if our reset value is 1, it's always going to be 0, 0. Okay, so then we get to our truth table, and this is where it can get a little confusing. So obviously here we have reset value, S1, S0 are two selector inputs, and then we have two what looks like outputs. So for our reset value, like we said before, if it's 1, right, our outputs are always going to be zeros. So that's what's going on there. So now that you know that, we can just ignore the bottom half because you know that everything's supposed to be 0 since the reset value is 1. If we look at this top bit, basically we're going through all the values that we have, right? So we have our 0, 0, we have our 0, 1, we have our 1, 0, and we have our 1, 1. And if we add another bit, we go to 1, 0, 0, and that's where we always, that's like going back to our first state, our state A. And then we have our two what looks like outputs. I'm not quite sure why it's exactly this, but it's going to be the same for a mod 8 counter as well. Just imagine we have another input S2, because as I said earlier, we're going to have 3 outputs and 3 inputs for a mod 8 compared to our mod 4, which has 2 inputs and 2 outputs. So this also is just what happens if it's plus 1, right? So if we had 0, 0 and we go to the next state, we're going to end up in 0, 1. If we went from 0, 1 and we added 1 to the whatever state we were, we'll go to the state 1, 0. And that's why it's just these 2 inputs plus 1, and that's what state we're in. So that's how we got this side for the first 4. And then I don't know why, but these two are just the same. Like these 2 columns are going to be the same. So just copy the same values over here. So now that we know that, you see these equations over here and you're like, how did we even get these equations? So for this, if you notice, this equation and this equation are the exact same, and this equation and this equation are the exact same, right? And that's because our 2 columns are the same. So our S0 and Q0, we have all the same values going down the column. So basically you can just do the math once and you'll understand. Like, you can just copy that value over. So how did we get this first equation? So we're looking at S0 and then to the plus 1, so next state, right? So if you notice, it's S1 and S0, and those are our 2 values, right? So this is all the right side of the column is actually our S0 values. So how we get this and this is that we look for where in our column we have 1s, right? Because that means it's true. And that's how we make our Boolean expressions. So here we have 1 in our S0 column, and we want to look at what in our inputs do we need to get 1. So our reset value is 0, S1 0, S0 is also 0. So if we just not all of them and add them together, we'll get 1. So that's why here we have not RT, not RT, not S1T, and not S0T. That's how we get 1, right? And then let's look at the next instance of a 1 in our S0 column. So for this one, we have a 0, 1, 0. So it's going to be not RT times S1 times not S0. And that's what we see here. Not RT, S1, not S0. And we OR these because those are like, we can either have a 1 in this state or a 1 in this state. And we naturally say 1 or 1. So that's why we have an OR here. So that's how we get this equation. And it's the same thing for when we're doing our S1. So we just look at the first column. And here we have a 1, so we get 0, 0, 1, not RT, not S1, and times S0. Not RT, not S1, S0. And then our next one is not RT, S1, S0. So we have not RT, not RT, S1, not S0. So that's what we have here. And then these are actually our equations. We're going to use the Q. These Q equations are what we use to come up with our wirings. But they look kind of ugly, so we can actually simplify these equations in order to make our wiring easier. If you notice, we have the not RT and not S0 in both of these, so we can factor that out. So we can have RT, S0T, both nots, right? And we'll factor that out of the equation and get S1T, the not, plus S1T, the regular version. So we haven't really, I don't know if we've covered Boolean algebra that well in class, but in this case, let's say that S1 was 0, right? And we're ORing it with the opposite of that, the complement. So that would be 1. 1 or 0 is always going to be 1. So in this case, this is always going to be 1. And 1 times anything is just itself, right? So we can completely ignore all this and just look at that. And that is our simplified equation now. In that case, we just got rid of another input that would have confused us. So this makes our wiring a lot easier if we only have to worry about 2 inputs instead of literally all of this. So how does that translate over to our logic design? So obviously you can see our reset input here, and if you noticed, for all our equations, they're always nots. So we just put a not here so that we don't have to worry about like knotting right before all the ands. And then here are our D flip-flops. So we have our S0, which, we noticed that S0 is one of our selector lines and S1 is one of our selector inputs. So these are our selector inputs, and as you can see, the reason why we're using a D flip-flop is that the output is always Q and not Q, right? So when we have our S1 and S0s, the only thing we have, only values we can have is either the nots or the regular version. So we have our not S1 and our S1, right? So that's why we only really need these 2 inputs, and the D flip-flops helps that be more simplified. So let's actually look at what's going on with these ands, right? So we have this and right here, and what values is it getting? So we're getting here, if we look at our first line, we're getting not S0, not S0. What's our other and? Follow that line, we're getting S1. And that's coming from the Q, not the not Q, so that's the regular S1. Sorry, that's S1. And what are we getting from the last and? Let's follow that line, the last item in and. We're getting our not reset. So we have RT, and we're getting the not of that. So that's what's going into this first and. Does this look familiar? Hopefully, right? Because for our Q0 output, if we go back up to the thing that I just, we were just looking at, this equation, we have our not RT, our S1, and our not S0. And that's exactly what's going into this first and. So as you can assume, this second and up here is going to be the other equation, not RT, not S1, not S0. And we OR them together, right? This is the OR gate thing, and that gives us our Q0 value. The interesting thing about our D flip-flop is that we have to store our previous values, right? Because the clock only works if you have the previous value to work off of, and that's why it was so important that we knew what state we were in. So from A, we can only go to B because we knew that we were already in A. So we had to take our output here and actually throw it back into our D flip-flop. And that's what we're doing here. So our D flip-flop gets a value, and then Q, not Q, and it gives us those values. And when we first run this, it'll actually set these values as 0, so it'd be 0, not 0, and we can build off of that. I'll go into D flip-flops in just a second. So if we look at our Q1, this is the same thing. This AND is going to be this equation, and this AND is going to be that equation, and we're ORing them together to get our value Q1 here that we also throw back into the D flip-flop. So now that we understand like how we get our new values, let's actually go into how a D flip-flop works. So this works best if you understand how an SR flip-flop works, because a D flip-flop is just a simplified SR flip-flop. So before, it's kind of hard to explain, but basically for an SR flip-flop, if we have a clock value of 0, it doesn't matter what our S or R inputs are going to be, we're actually storing that value into memory. And this makes sense if you think about it, because we can only work off of a value that's stored, right? As I just said, we need to know the previous state in order to go to the next state. So here, if our clock value is 1 and we have an input of 0 and 0, that's also saving it to our memory. Move on, if we add 1 to our bit, 1, 0, 1, that's going to give us 0. 1, 1, 0, that's going to give us 1. And then 1, 1, 1 is our invalid state. So our circuit looks like this. We have an S input, an R input, and it's going to do some math inside of there that's going to give us a QN output and not QN output. And that's our outputs here. So what happens in a D flip-flop is that we're only getting one input called D, which stands for data, right? And we're just going to assume that we're going to do the math, and we're going to actually know our S value because it's going to be the opposite of we're going to know our SR values because they're based off of the D value. So just like above, how for 0, it doesn't matter what we get for our S and R because it's going to store in memory. For our D value, it doesn't matter what our D value is going to be because it's going to store that value in memory. And so if we went on to our next one, if we get a D value of 0, that's actually the same as this bit right here. So D equals S, which is equal to 0, right? And our R value is actually going to be our not S, which is equal to 1. So that's the same as having an S0 and an R value of 1. So if we go back up, S0, R value of 1, that's going to give us an output of 0. So that's what's going on here. So same thing for the next one. If we have a D value of 1, that means our S value is also going to be 1. And then our R value is just going to be the complement of S, which will be 0. And if we go back to our S0 truth table, 1, 0 gives us 1. So that's why we have 1 here. So instead of having a bunch of different values and inputs we have to worry about, the D flip-flop is super simple. It also gets rid of this invalid state where we'd have too many inputs and it doesn't, it breaks. In an SR flip-flop, if we had 1, 1, 1, it'll break. D flip-flop, we don't have to worry about that. And it'll even save value to the memory when needed. So here we had our S flip-flop, S input, R input, which gets simplified to S is D and R is the complement of D, right? So that's what that not's doing there. So basically, we only need one input. So that's why it's D, and then QN, not QN. So going back up to the circuit, we have this flip-flop going on here. And I need to explain how that works because it's confusing. So let's say we start with a D value of 0, right? So here we're going to get a 0, and here we're going to get a 1, and our clock input is 0. So 1 and 0 is going to give us 0. And we're going to get that value. It's going to go here. It's going to be 0. And then here, it looks like we're grabbing the value from over here, right? We don't have a value here yet, so that's actually going to be 0 too. So it's going to be 0 and 0. If we OR 0 and 0, we're still going to get 0, but then there's a not. So that's going to turn into a 1. So our not Q becomes 1. So now we're going to go to the second part of the circuit, because, you know, I only worked on the first AND. If we go to our second AND, right, we get 1 and 1. If we AND them together, we'll get 1. Right, so then that goes into our NOR gate. We have our 1, and this is going to grab here. This input is coming from here. So we do have a value for that. It's 1. So we're going to grab that value. And that's going to be our 1. So or 1 is going to give us 1, but we have our not, so that's going to give us 0. So Q is 0. How do we know this worked? Because obviously these two are complements. So as long as these values are the opposite, we don't have to worry. That means our D flip-flop worked. So let's say our D value is now 1. All right, this is going to change some stuff. So if we have our D value of 1, this is going to be 1, and this is still going to be 1, right? So 1 is going to give us 1. And then we're going to bring that 1 over here, and then we're going to grab that value 0. So 1 or 0 is going to give us 1, but it's the not. So that's going to give us 0. So our Q, not Q, is now 0. Let's go to our second AND gate. So if this is 1, it goes through the not, we're going to get a 0. So this is going to be a 0. And then our 1 is still the same from the clock input. So 0 and 1 is going to give us 0. We're going to bring that 0 over here. So now we're at our NOR gate. 0 or 1 is going to give us 0 or 1 is going to give us 1, except we're ORing it. Oh shit, no. It's not 0. It's not 1 here anymore, remember? We have to grab our new value of 0. So 0 or 0 is going to give you 0. Ignore all that. But we're